Today we discuss the case, the non-interacting case, like the integer quantum Hall effect and the geometric field equivalent of the integer quantum Hall effect, namely the Chern insulator. And we have derived the entanglement spectrum when we cut the system into two parts. We have seen that the entanglement spectrum will actually mimic the edge mode of the integer quantum Hall effect. By that I mean, if you look at the entanglement spectrum, the counting that you get for each momentum sector is actually the one of the chiral edge mode. And it's more than just the counting. If you look at how the entanglement energies, the psi will depend on the momentum, you see that there is a linear relation between the two. So it really mimics the spectrum in its full glory, not only the degeneracy, but also the dispersion relation. So the nice feature with the integer quantum Hall effect is the calculation is somehow simple to perform. You can do that analytically, at least part of it, because it's a single Slater determinant. So now if we want to look at a more complex system like the Laughlin state, the calculation is going to be much more tricky. So first I would like to remind you some results and notations about the fractional quantum Hall effect. So I think, well, you have seen that during the lectures by Karian, and also yesterday we work in the lowest Landau level, and if you use a symmetric gauge on the plane, the wave function are just the z power m, z square over 4, the phi m z, up to some factor that encode the normalization. When you want to perform numerical calculation for the fractional quantum Hall effect, you can use different geometries. So you can consider particles on the plane. That's the simplest thing to do, or the closest thing that you can imagine to the experimental system. But it's not always the simplest geometry you can consider. The simplest one is actually the sphere. So the sphere will be, it's a bit tricky because you need a magnetic monopole at the center. The flux is quantized. So is the area of the radius of the sphere. It's related to the number of flux quanta that goes through the sphere. And you can write down the wave function for the sphere. Just m, and we'll go from minus n phi over 2 to plus n phi over 2. And in the lowest Landau level, it will just be up to some constant u to the power m, v to the power n phi minus m, where u and v are the spinor coordinates on the sphere. It means that if you put some axis z here, got some point on the sphere, get a theta angle and its projection phi, u and v will be just u is cosine theta over 2 exponential I phi over 2, and v equal to sine theta over 2 exponential minus I phi over 2. Right, n phi is the number of flux quanta, and m is the angular momentum. It's still like the LZ quantum. It's the LZ quantum number that can, if you're on the sphere, remember it's like a spin, so it's an angular momentum. It goes from minus L to plus L. Minus L to plus minus L to plus L, sorry. Okay, good. So that's the two cases we will look at when we will show you numerics about the entanglement spectrum for the fractional quantum Hall effect. Don't be scared by the sphere geometry. You can always go from the sphere to the plane and vice versa using the stereographic projection. So you can relate the two by the stereographic projection. Roughly speaking, what you will do, up to some factor, you have to take care of the Gaussian term, but imagine that in your wave function, remember that when you write down a many-body wave function in the lowest level, it's so on the plane, it's a polynomial in the electron coordinates times the Gaussian weight. That's the number of electrons. So mostly we will, for the time being, forget about this Gaussian term and focus on only the polynomial part. So if you want to go from here to the sphere, what you have to do is basically to replace z by u over v, up to some additional factor, depending, which is just a v to some product of the v to some power. But at least we should, even if we work with the sphere, you can always write down your wave function on the plane and translate from the plane to the disk by using the stereographic projection. Okay. Good. So let me. So remember the Laughlin state. I just dropped the Gaussian term here. So you have seen that you can create bulk excitations in the system by adding flux quanta. Basically, if you add one flux quantum to your system, it's like adding one quasi-hole to the system. So that's, you can write down the wave function for the Laughlin state plus one quasi-hole, just be the product, let's say one quasi-hole at coordinate z0, product of I, this is plus one QH times the Laughlin state. So of course you're free to put your quasihole wherever you want. But if I say in my system that I have a given number of particles, so let's say you fix n and phi, which will be on the sphere here just m times n minus 1. So that's the number of flux quanta that you need to realize the Laughlin state. I think you saw that in Karian's lecture, plus one flux, because you add one quasihole to your system. You can wonder how many wave functions I can write down. Well, that's if you fix the position, there is a single wave function, but if you're free to move it, there's a finite number of wave functions that you can write down. This number of wave function is basically if you develop this as a function of if you develop this wave function with respect to z0, you will have a bunch of polynomials. And how many do you have? Well, you will get n plus 1 polynomials. They are all linearly independent. If you check when you decompose, for each of them, they have these polynomials have different momenta. So they are by construction orthogonal. So they are all linearly independent. And you can wonder how many, so let's say now I add more and more quasiholes to my system, how many wave functions I can write down. Well, there is a simple rule to obtain this number, which is you can use the Haldane's exclusion principle, which will allow you to compute this number. So basically, the rule of the game is the following. You have n particles and n5 flux quantum. One, two, three, 4, 5, and I need one more, 6. So there I have 6 flux quantum in my system, and let's say I have 3 particles. 6 and n is equal to 3. The rule of the game is the following. You have 3 particles that you can put, you can create any configuration here that involves 3 particles, but it should obey the following rule. No more than one particle in M. Here we look at the Laufin state 1/3, so we take M equal to 3. In M consecutive orbitals. So for example, this configuration here, so I put 3 particles into my 7 boxes, is forbidden. Because here I violate this rule. I have 2 particles in 3 consecutive orbitals. So the only option that you have actually for this specific number of flux quantum and this number of particles is this configuration. That's the only option. And, well, this is exactly the relation between the number of flux quantum and the number of particles where you get the Laufin state. Right? The Laufin ground state will occur when you have n phi is equal to, so for the filling factor 1/3, it's 3 times n minus 1, and you can check that you get 3 minus 1, you get 2 times 3, you get 6. So that's why it's there is a unique state, densest energy state from that exclusion principle. If you now want to look at quasi-Hall excitation, you just have to increase the number of flux quantum. So let's say you look at still n equal to 3, but n phi is equal to 7. Then you have one more box. 0, 1, 2, 3, 4, 5, 6, 7. Now I have many more options. I can do something like this. So let me just, I can do that, or this, or that. These are the only 4 configurations that you can write down that satisfy this principle. States. Remember when I've written down the polynomial and decomposed as a function of z0, the power of z0, we had n plus 1 polynomials. So here you have 3 particles, so you expect 4 states, and that's exactly what you get. So you can play this game for any number of particles and any number of flux quanta. So you can get this number just by using this rule here. When it comes to the edge excitation, you know that the edge excitation are of the same nature than what you have for the integer quantum Hall effect. You can also count how many states you will get. And like we use this exclusion principle here to get the bulk excitation, you can also count the edge excitation exactly the same way. So the rule of the game is you should not have more than one particle in 3 consecutive orbitals. So this will be the zero energy state of your edge mode, right? These are empty orbitals and these are occupied orbitals. Now I can do the following. So this is the E equal to 0 for the edge mode. The first excitation, I can promote, for example, this guy here. That's one option. Right, that's the energy, that's the momentum K, or LC. It's exactly the same thing that we have done yesterday. Of course, I cannot. It's this one is an you can. It's a move that you can perform, but you cannot do that. So this one is okay, right? You still satisfy this exclusion principle, but you cannot promote this guy here to here because you will have a violation here. You can play the game and count how many states you have per energy level, and you will see that you get exactly the same numbers that we had yesterday. Remember the series where you have 1 state at momentum 0, 1 state at momentum 1, 2 state, 3 state, 5 state, and so on. So the counting for the edge mode of the Laughlin state, whatever the value of m, including m equal to 1, you get exactly the same counting. So far, so good? So now we have all the tools to count stuffs in your Enneagram spectrum. So the calculation that we have performed yesterday for the integer quantum Hall effect, meaning to cut the system in real space, you can also do that. It's also doable for the fractional quantum Hall effect. The major problem here is if you take the Laughlin state or any of the fractional quantum Hall states, you have to decompose that on a basis, right? M lambda, where the M lambda is just the Slater determinant where you put z1 to the power lambda 1, z2 to the power lambda 1, and so on, zn to the power lambda 1, lambda 2, and so on. Sum over all the lambdas. So that's for the fermionic state. So yesterday it was quite simple because this sum was just a single term. So we were able to do the calculation. But imagine that the calculation that you performed yesterday for a single determinant, you have to repeat it and build a full density reduced density matrix out of that. So actually, there is no way to do the calculation analytically here. You need to rely on a computer to perform this calculation. And moreover, the real space Newman spectrum is actually quite, I don't say it's not doable. It's of course perfectly doable in terms of numerics, but there is actually a simpler way to cut the system that will give you this similar results. And it's called the orbital entanglement spectrum. Or OES. The idea is the following. Remember, when you use the symmetric gauge, your orbitals look like that. You have m equal to 0, m equal to 1, m equal to 2, m equal to 3, and so on. So now let's say you want to cut your system into 2 in real space. Well, you can make a sharp cut. That's exactly what we have done yesterday. We have decided, okay, let's cut the system like this. So there's going to be the region A, and the other one is going to be the region B. But you see that the orbitals themselves, they give you already some kind of real space partition. Basically, if I keep the orbitals 0 and 1, it's like an approximation of the area of the region A. So instead of cutting in real space with a sharp cut, let's just keep orbitals. It's exactly what we have done for the spin chain. For the spin chain, the cut is it's a cut of the lattice. So you say, oh, the part A is going to be this, all the spin from 1 to 10, and the part B will be the remaining spins. So you can do that here for the orbitals. The nice feature of the fractional quantum Hall effect is when you work, you can think about going to real space, momentum space. You have this duality once you project onto the lowest Lambda level. So actually, this kind of cut was introduced not in the for the orbital entanglement spectrum. First, it was introduced by Kalian and coworkers to compute the entanglement entropy of the Laufendt state. So instead of cutting in real space, they have done is to cut in orbital space. Okay, so if you look at a given configuration, like this one, for example, we will say, okay, let's keep the orbitals from 0 to 2. This is going to be my part A. And the remaining part will be the part B. And approximately, it's like cutting your system in real space. And in terms of calculation, it's actually much simpler to do that numerically than to do the real space cut. So if you remember yesterday, we have already talked about this way to cut the system into two for the integer quantum Hall effect. For the integer quantum Hall effect, you have a product state, which means that all the orbitals are occupied. Which means that the state itself is already a product state. You can, if you decompose into one, it's just, that's the A and B. There is no sum here, so there is a single non-zero eigenvalue, which is equal to 1, and the spectrum is trivial. So you don't extract any information for the integer quantum Hall effect if you cut like this. But as soon as you have a filling factor that is lower than 1, you have enough freedom, and it's interesting to look at this kind of cut. So let me show you what you get if you do the calculation for the Laufendt state. So yesterday I drew everything by hand. Right? Today I will just use slides. It's much more convenient. So this is the orbital entanglement spectrum for the Laufendt state 1/3 on the sphere, but honestly, if you think this is the plane, you get exactly the same result. I will, like yesterday, remember what we have done is to look at a specific sector of the number of particles in A. So here I will take, it's the entanglement spectrum, the total system has 12 particles. This is the entanglement spectrum when I look at the sector when Na is equal to 6. So it's like half of my system. And I will keep half of the orbitals. So if I have a sphere, it's like cutting my sphere like this. It's really cutting into two equal parts, A and B. And I look at the sector where the number of particles is actually equal to half of the number of the particles of the original system. I can plot the entanglement energies as a function of the angular momentum. And I will get the following counting. As you can see, it's 1, 1. You have a zoom here. 1, 1, 2, 3, 5, 7, 11. So when you do the orbital entanglement spectrum of the Lofgren state, you recover exactly the same counting that the counting of the edge mode of the Lofgren state 1/3. So that's the simplest example that you can imagine for of a fractional state where you can do the entanglement spectrum. And once again, we obtain what we have obtained already previously for the integer quantum Hall effect, or even for the AKLT state, namely that the entanglement spectrum gives you access to the excitation of the edge of your system only by looking at the bulk state. So of course, we would like this to be linear. You have some dispersion, but remember yesterday, even for the integer quantum Hall effect, to get exact linear dispersion relation, it's only when you reach the thermodynamical limit, so for when you have a very large number of particles. Otherwise, you have finite size effect that will, here, for example, this region of the spectrum, it's not the edge mode that you're counting anymore. It's just a finite fact. You're probing the fact that your system has a finite size. So the Hilbert space is constrained by the finite size effect. And moreover, the levels are not strictly degenerated, as it should be for the true edge spectrum. You have a splitting, but once again, it's a finite size effect. One thing I did not mention here, for example, for this value of LZ, you have a single state. Remember, we look at a system where we have a given number of orbitals, a given number of particles, and a given momentum. Here, L is equal to 0. The number of particles is half of the number of particles we have in the system, 6. And the number of orbitals is actually half of the number of orbitals that we have here, which should be of the order of 16. So if you try to see how many states you can build if you have 6 electrons in 16 orbitals with a total angular momentum of L is equal to 0, you will see it's a large number. It's not a single state. It's a very large number. And it's a number that will increase exponentially with the system size. But still, whatever you do, if you increase the size of your system and you look at this sector of the entanglement spectrum, you will always get a single state here. So remember the story of the AKLT model. It was exactly the same picture. We had two levels, whatever the size of the chain we were looking at. So there's a massive reduction here. The number of 0 eigenvalues in your reducibility matrix is actually it grows exponentially with the system size. But so are the non-zero levels. Of course, it's a ratio between the number of 0 eigenvalues that you have in your reducibility matrix versus the ratio of non-zero eigenvalues. Like what we have done for the AKLT model, we went away from the pure AKLT point and look at the Heisenberg model. Here you can do exactly the same. Remember, the Lofgren state is just a very good approximation of what's going on at 1/3. If you take a more realistic interaction, like the interaction that you can imagine you have in your 2D electron gas in an experimental sample, well, the interaction is much more complex. You have first, it's a longer range interaction. It's basically the Colomo interaction. You can have some screening. You have some effect with the fact that it's not really a 2D system and a finite thickness. All these ingredients makes that, well, the Lofgren state is just an approximation, not an exact ground state. So in terms of microscopic numerical simulation, it's quite easy to replace the model interaction and give you the Lofgren state by some other interaction, like the Colomo interaction. So keep the filling factor at 1/3, keep the same number of particles, and just replace the interaction and compute the ground state using exact diagonalization, for example. Once you have this ground state, you can perform the entanglement spectrum. Here, what you have, the value of LZ is a bit shifted compared to the one I've shown you before, but it's just a shift in the calculation. There's nothing, no big deal here. So the first thing that you observe is there's like a low branch here, And the low branch actually has the same counting that you have for the Lofgren state. You will find back the 1, 1, 2, 3, 5, 7. Of course, like for the Heisenberg model, you don't get only that. You get also some higher levels, higher energy levels, like this group here, this group here, this group here. So the claim is, if you move away from these model states, being the Lofgren state, but it can also be the Moore-Reid or whatever wave function that you build, for example, from CFT. If you move away from this model state, like you move away from the AKRT model, well, the entanglement spectrum will get some levels coming down from infinity, but still, if the low energy part of your spectrum has a gap, it's a gap in the entanglement spectrum, not an energy gap, then you will say that, well, your system is, the universal properties of your system are dominated by this universal part, which is in that precise case the Lofgren state. So maybe now let me show you some yeah. I'm sorry, I mean, yesterday we went through mathematics, like I wrote lots of formula. Here today I will show you lots of plots, so I apologize for that, but I mean, I have to show you how it looks like. As you can already see here, well, you have this Lofgren structure emerging in your Coulomb ground state entanglement spectrum, but you also have additional structures here. Actually, if you look for a smaller system size where it's a bit simpler to observe everything what's going on here. So here is the Lofgren structure. Again, you have like a first structure here, another one here, another one here. So that's a question that was asked yesterday afternoon about what's going on if you don't look at the zero temperature problem, but like if you have some temperature, and so you have to include excitation. If you start from the Lofgren state, and you do the entanglement spectrum for this guy, so you compute the density matrix just as a projector onto the Lofgren state, you trace out blah, 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 you get the entanglement spectrum of the Lofgren state. Now let's say you put some Boltzmann weight, and you sum over the projectors, the right weight of the energy. Well, what you will see is something like that. So let's start from the Lofgren state plus some non-zero temperature, and you will, if you include the first excitation, you will find back once again the Lofgren structure, and a first structure that actually is identical to the structure that you find here. My point is the following. If you move away from the model states, so the model states are very specific in this exponential reduction of non-zero eigenvalues. If you move away from the model state, you still have a fine structure going on there. The low energy part will be driven by the universal part. If you look at the higher part, the non-universal parts of the entanglement spectrum, you can relate these structures also to the excitation of your system. The excitation that I've included here is just the simplest excitation you can imagine on top of the Lofgren state. You don't change the number of particles, you don't change the number of flux quanta, but you can create a pair of one quasi-electron. That's the lowest energy mode in your energy spectrum. If you include these guys into the calculation of the OES, this is what you will get. So there are lots of information that you can extract from the entanglement spectrum. Not only the information about the ground state excitation, but also some of the higher level excitation. So far, so good? It's just, I didn't include, too bad. Let me show you one thing that will be helpful for what I will talk about after the break. So when you do the OES, you can do that on the sphere, on the plane. You can also use another geometry, which is the cylinder, for example. So let's say it's LZ or K, as you prefer. So if you do the calculation for a cylinder, the perimeter of the cut is just the perimeter of the cylinder. And you will get exactly the same structure. So the shape of the entanglement spectrum might change. It might change a bit compared to the to what you have on the sphere geometry. So what is important here is the counting, not the shape. But what you will see, for example, when you change the perimeter of your cylinder, so keep the same number of particles, the same number of flux quanta, the same way to cut the system. So I'd say I look at Na equal to n/2, but let's change the perimeter of the cut. What you will see is that basically, depending on the perimeter, the slope of the entanglement spectrum will change, right? If you go to a thinner torus, so if you decrease L, the slope will increase, and vice versa. I mean, if this is an edge mode, remember that the dispersion relation was as a function of the angular momentum. That's what we discussed yesterday. It goes like 1 over the perimeter. So it's not surprising that if you decrease the perimeter, you increase the slope of your entanglement spectrum, if the entanglement spectrum is mimics the spectrum of the edge mode. Good. Any questions? Yeah. It does not when you look beyond u equal 1/2. And I will come back to this point after the break, because I will show you why this one gives you the exact counting for the edge mode, like mathematically why it gives you the right results. But you're right. So that's one thing, maybe the right moment before switching to another way to cut the system. Remember, so yesterday we discussed the real space cut. Here we discussed the orbital cut. If you look at the 1/3 state, you will get the same kind of information. If you look at the integer quantum Hall effect, you see that in one case you get a trivial result, in the other case you get information about the edge. So I think the key point here is you have many ways to cut your system, and depending on the way you cut, you might extract different type of information about your system. And sometimes if you get a trivial result, well, maybe it means that you have to change the way you cut your system into two. So moving to the, that's a good reason to look at another way to cut the system into two. So this part was the part 2, the orbital entanglement spectrum. So this one is the particle entanglement spectrum. The next one I want to discuss. So right now what we have done is really to cut the physical system into two separated parts, right? Region A and region B. But if you think about the orbital cut, it's already less clear what it is exactly. It's almost that, but it's actually more a cut in momentum space. The thing is that for the fractional quantum Hall, momentum space and real space are related. So there is another way to cut the system into two, is basically you don't change the geometry at all. You preserve the geometry, but you just remove particles from your system. So you can compute a reduced density matrix, which is like this. Let's say I want to remove n. So remove n minus na particles. So that's the way you trace. You perform the trace over B. You just integrate out over n minus na particles. So na plus 1 And now I just use projector, and hope I won't. Yep. Plus 1 dot 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 Rn times psi of R1 prime dot 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 Rn. So I pick Na particles, let's say the first Na particles, and I integrate out on the remaining particles, so from Na plus 1 to n, right? It's a matrix where you have two entries, the R's and the R primes. If you open a textbook about thermodynamics, for example, and you look at the definition of a reduced density matrix, this is what you will find. So there is nothing surprising here. So you see, that's another way to cut the system into two. We didn't do anything to the geometry, we have just removed particles from the system. Let's say you start once again with a nu equal 1. So the nu equal 1, remember, you have all orbitals are occupied. So if you look at the entanglement spectrum, the particle entanglement spectrum of this guy here, how many levels do you get? Well, it depends how many particles you remove. Basically, if I remove n minus Na particles, I can choose any of, I will keep Na of them. So I can keep, for example, this one, the first one, the third one, and the last one. Or I can take any of the possible combination. Right, so you see that for the particle entanglement spectrum for the nu equal 1 won't be trivial. And you can actually count how many levels you will get in the entanglement spectrum just by some combinatorics here. It's just a number of ways you can pick Na particles among the n particles that you have in your original system. You can also do this kind of calculation for the Florence state. And if you do that, this is the kind of spectrum that you will get. So let me, once again, you can plot, you look at, here the number of particles is fixed, right? This is the way you cut your system. So you say, I keep Na particles. So there's a single block in your reduced density matrix. And I can plot as a function of the angular momentum. When I remove particles, I don't break any of the symmetry, of the geometrical symmetry of my system. So I get, if I work on this here, I still get the full rotation symmetry. So I can use LZA as a good quantum number, but actually you see that you have a massive degeneracy here. It's just the fact that your system is rotation invariant, not only around the LZ axis, but any rotation. Once again, when you do numerics, when you see massive degeneracy like this, there's a high chance you didn't take into account all the symmetries. So you should do that. It's really helpful. Anyway, so this is the kind of spectrum that you will get. Once again, if you pick a given LZ sector and you wonder how many levels you should get a priori if you take a random state, it will be much more than that, exponentially bigger than that. So there is also like a massive reduction here. So the number of states that you get per LZ sector actually matches the number of quasial states that you can build with Na particles. So the PES, counting of the PES, the particle entanglement spectrum, is the counting of bulk quasial states. Remember, I gave you this rule to count how many of them you have. If you want to apply, you do the calculation of the particle entanglement spectrum for the Delfino state, and you check that you get the proper counting. It's actually, it sounds, so the first thing that It should ring a bell. If you get the same counting, there's a high chance that what you observe here are actually the bulk excitation of the system. And actually, you can go beyond the just the counting. If you look not only at the levels, but remember when you look at the Schmidt decomposition or the reduced density matrix, you can look not only at the spectrum, but you can look at the eigenstates of the reduced density matrix, or the AI here. If you look at the eigenstate of the reduced density matrix for each of this level, these are actually the quasial state, the bulk quasial state, the full quasial state, the full polynomial. So it means that if you start only with the ground state and you remove particles, you get access to the bulk excitations of the system for a reduced number of particles, sure, but you get access to the bulk excitation. To show that for the Laughlin state, it's actually trivial, well, more or less trivial to show that these guys for this spectrum are quasial state. To prove that you get all of them and that there is no accidental reason that some of them might disappear in the process, is actually there is no mathematical proof of that. So it's not that a trivial statement. So you see, we have used the orbital entanglement spectrum of the real space cut, and we observe the edge excitation. We have looked at the particle entanglement spectrum, and we have access. We have been able to address the bulk excitation of the system. Once again, only by looking at the ground state. We didn't do any numerical calculation to access the edge excitation, just for free from the ground state wave function. So let me just give you the maybe move up. Let's see. I want to address one point here. When you do the calculation on a torus geometry, remember that you're looking at topological phases, like non-trivial, non-SPT phases. So when you change the genus of the surface, you increase the degeneracy of the ground state. So if you take a torus now, well, the Laughlin is M-fold degenerate. So it's also a question that people ask me, what should you do when you have more than one state? It was already the case for the RT model. Remember, we had 4 states. So what we have decided is to pick one of them and to look at the entanglement spectrum. If you do the real space or the orbital entanglement spectrum on the torus by picking a single state, basically what you will see, you see that if you cut your system into 2 here, let's say like this, you will create 2 artificial edges. So if you look at the entanglement spectrum as a function of the momentum, you will get the many-body spectrum that you build from 2 counter-propagating chiral edge mode, which means that you will get one state at momentum 0. At momentum 1, you can plus or minus 1, so you get here or here. At momentum 2, you've got 2 states here, 2 states here, but I can also combine these 2 guys to get the same energy. So you find this diamond structure. So that's exactly what you observe when you do this calculation for Laughlin state on a torus, but you pick a single state. For the particle entanglement spectrum, you can actually you do the following. Right now, what we have done is to look at the entanglement spectrum of a single state. And we said basically that the density matrix was just a projector onto the single state. Then we trace out and get the reduced density matrix. But now if you take for the full density matrix, let's say your state is D-fold degenerate. So you take your D degenerate state and you compute the this projector onto the ground state manifold. If you do the PS on this guy, you will get exactly the same property that you have on the sphere, namely that the entanglement spectrum will be like this. You will get as many levels as you have quasi-Hall state on a torus. And on top of that, since you don't break any symmetry here, the momentum is still a good quantum number. You can, if you move away from the Laughlin state, you do the particle entanglement spectrum, but you don't look at the Laughlin state, you look at the Coulomb ground state at 1/3. Like we had for the orbital entanglement spectrum, well, once again, we have a low energy structure that exactly is equivalent to the one that we have for the Laughlin state 1/3. We have an entanglement gap and higher energy levels. You can also relate this higher energy levels to some excitation of the system, but it's like a nice way to say, okay, well, the Coulomb ground state is dominated by the physics of the Laughlin state. So 3, 4, so now let's do the real space entanglement spectrum. The calculation to get the real space entanglement spectrum is exactly the same calculation that we have performed for the integer quantum Hall effect. So you use exactly the same technique. It's just a bit more tricky because now you don't have a single such determinant, but thousands of millions of them. But the procedure is identical. So if you do that for the Laughlin state, I go back to the sphere geometry. This is what you will get. Once again, you have the spectrum, the counting is the one of the edge mode, and so on. It's actually quite interesting. You can, for example, look at the splitting. I've told you that in finite size, you will have a splitting between the states in a given momentum sector. It's not like exactly like the edge mode, but you have perfect degeneracy. And you can look at how it scales with the system size. So that's the first example where you have 2 states, and you will see that this will converge to the same value. You can do that for the other levels. And basically what you observe is 2 things. So first, when you do the extrapolation, the splitting will go to 0. And then the difference of energies when you increase the momentum, well, somehow the entanglement levels, something that is linear with the momentum. Basically, you see that the spacing here is here, and here is the same. Here it does not converge yet, but you get I think the correct idea. So you can do that numerically. You can check that. Well, you will recover really the edge mode out of that. Right now, it sounds like we have very different ways to cut the system, but actually there are some non-trivial relation between the particle entanglement spectrum, the orbital entanglement spectrum, and the real space. Let me just maybe mention that before the break. Actually, the simplest thing that you can relate is the real space entanglement spectrum and the particle entanglement spectrum. Remember, we talked about the entanglement matrix. I've told you that if you have a state and you can decompose it onto UA, so you have a base for the A part and the B part, and you have the entanglement matrix MUA, UB times MUA tensor product MUP. This is all you get. You do the SVD on the entanglement matrix, and you get the entanglement spectrum. What you can show is that the entanglement matrix for the real space cut is actually for a given number of particles. Remember that for the real space, you don't, in principle, you can have all your particles in A. So let's focus on a single block of the entanglement matrix. The entanglement matrix is block diagonal with respect to NA. So the two entanglement matrices, the one of the real space cut and the particle entanglement spectrum, are actually related just by a simple transformation. So the two entanglement matrices are just identical up to some multiplication by diagonal matrices. The diagonal matrices are just some of the weight of the full orbital, one on the A side and one on the B side. Right. You remember yesterday when we have split the orbitals into some wave function A and wave function B, where this S and Q are just the NA and NB we've talked about. So this, as a first consequence, is the rank of the matrix, which tells you how many non-zero eigenvalues you have in your resistivity matrix. If these are diagonal matrices and they have no zero element on the diagonal, so you won't change the rank by this transformation when you conjugate the PS by S and Q. So the rank of the real space cut and the rank of the particle entanglement of the entanglement matrix for the particle cut are identical, so they have exactly the same number of levels. So the number of levels that you observe here is actually identical to the one of the real space. So I've told you that, wait. The particle entanglement spectrum should probe the bulk physics, and the areas, the real space, should probe the edge. Well, that's true, but you have finite size effect, so the real space will definitely have a region that probe the edge physics, and this region will increase when you increase the system size. The particle entanglement spectrum, actually, if you look at the number of states that you can build, bulk quasi-Hall state that you can build, the counting at the beginning is also identical to the counting of the edge mode, for a good reason. That's the argument that, let's say I work on the sphere, and I add a bunch of quasi-Halls at the south pole. So I will deplete my electron gas, like completely here. So the south hemisphere will be completely depleted. So from that point of view, what I've realized here is like a disk. So now if I increase a little bit LZ, it's like looking at the edge excitation around this disk. So it's not surprising that the counting in this region of the particle entanglement spectrum actually is identical to the counting of the real space entanglement spectrum. So that's one side of the particle entanglement spectrum. The other side is that I completely deplete the north hemisphere and I play exactly the same game. Of course, when the bulk of the spectrum here, it's not related anymore to the counting of the edge mode. You're just probing the bulk physics there. Okay, so I think it's time for a break. And after the break, I will show you one application quickly. And then I will try to provide some more mathematical background to this story of entanglement spectrum for fractional Colomo state. So let's resume in 10 minutes. This business of entanglement spectrum is, what do we learn more than we used to know about these wave functions? I mean, somehow if you think about the Laughlin states, well, if you think the bulk edge correspondence for the CFT is working, then, well, we know that you can get information about the edge by looking at the bulk and vice versa. So the first answer to that is, well, somehow the entanglement spectrum is a way to reverse. So usually what you do when you write down your bulk wave function from the CFT, you say, okay, this is a CFT of my edge, and from that I built the bulk wave function. Now, if you give you the bulk wave function, I ask you to build what is the CFT for the edge. You just use the entanglement spectrum. Of course, in principle, you have to go to an infinite size system to be sure it's the proper CFT, but at least give you a good indication of what you should get. So that's the first application, if you want. The second one is, imagine that you have a system where you don't have the wave function, or you don't know how to write the wave function. A recent example was the story of chain insulators when you turn on strong interaction. So it's like the fractional quantum Mole effect. In the fractional quantum Mole effect, you start with your Landau levels. Imagine that the gap, the cyclotron gap, is large enough, and you crank up the interaction, so there is no Landau level mixing. You crank up the interaction, and at some point you enter into the regime of the fractional quantum Mole effect. You can do the same game with a chain insulator. Take your chain insulator like this one, for example, the Kagome model, for which you have 3 atoms per unit cell. You have 3 bands. 2 of them have non-zero chain number. Take the lowest one, partially fill it, turn on strong interaction, and look at what's going on. Well, you will get the Laughlin state. And how do you know that? It's actually not that trivial to be sure this is the Laughlin state. For a long time, people didn't know how to write down the wave function for these models. It was kind of a tedious work to be able to do that. But if you look at the particle entanglement spectrum, which is quite simple for this calculation, it's exactly the same story. You don't change the lattice, you just remove particles from your system. You have the ground state wave function. You do excitonization on this chain insulator with strong interaction. You do the PS, and once again, you plot as a function of the quantum of the momentum. You plot the entanglement energies, and you observe this low energy structure, the blue one, and some high energy level. And the blue one, you can count how many states you have per momentum sector. It's exactly what you expect for a Laughlin state. It is the number of quasi-Hall states for given number of particles, given number of flux quanta, and you have a perfect match, and you have this big entanglement gap. So even just by looking at the particle entanglement spectrum, you know that the physics of this system will be driven by the Laughlin wave function, or the Laughlin state. It's not, what you get is not exactly the Laughlin state. You have some higher energy level, but still it describes the same physics. Okay, so that's one application of this business of entanglement spectrum, to probe system where you don't know how to compute overlaps, but still you know properties of the state that you want to observe or that want to emerge. So in the last half hour or so, I will try to give you some insights why we have this property for the Laughlin state, namely why we have this entanglement spectrum on the more rigorous ground. There's also another motivation for that. Remember that the entanglement spectrum, even if you think about the orbital of the entanglement spectrum, you have a massive reduction of the number of levels, right? So when you have that, you know that there should be a good matrix product state description of your state. And maybe, so this story was initiated by 2 guys in 2012, Zelatel and Mong, and I want to stress that Roger Mong was a postdoc at that time, and Mike Zelatel was a PhD student. And if you look at the article, it's a really nice one. And so if you're able to, as a PhD or as a postdoc, to write such an article, well, it's a good job. Okay, so how do we go from the model wave function to the MPS? If you use conformal field theory, that's what you have seen in Karian's lecture, you can rewrite your model wave function. So let's say you have any electron. I will use any and not n, as I've done previously, because I will use another n. So CFT, and I will focus on the Laughlin state. So let's use a CFT description of the Laughlin state. M phi 0, then you have the product of vertex operators V Z1 to V Z N E. Did you introduce the background charge? Yep. Okay, so you know this guy. This is the background charge that will just make that your system is electric, as a zero charge at the end. Just these are the two boundary conditions. And the VZ, just to remind you, this is the vertex operator. Exponential I square root of M phi Z, where phi Z is just a chiral field. It's corresponding to, it's the holomorphic part of the massless free boson. So you can do the mode expansion for phi Z, zero mode, 0 log Z plus I sum over n different from 0, 1 over n a n Zn. It's just a mod expansion, right? And with the commutation relation between the creation and annihilation operator, which is an am, or let's say n prime, so we don't mess with the, so it's n delta n plus n prime 0. Okay, so A0 will measure the charge, the U1 charge, which is the actual charge up to some square root of 1 over square root of m. So you can build, this is an operator, to it act on some Hilbert space. So that's a CFT Hilbert space that you can, on which this operator will act. So you start with the primary states. So the primary state, you just act with the phi 0. Basically, you start from the vacuum and just increase the charge. That's exactly what this operator will do. Remember that, well, maybe I should also say that the commutation relation between phi 0 and A0, it's just I. So they are canonical conjugate variables, right? So it's like the momentum and the position. So if you think about momentum, basically if you take exponential of I times the x, you increase the momentum by 1 unit. So that's exactly what this operator will do, but not on the position, on the momentum, but on the charge. Right? This is for the cat. For the bra, it's a bit more. If I want to be super accurate, this is what you should do. Square. I hope I don't screw up the factors here. You will find references in my notes. But basically it's just this. Over square root of m phi 0. So you can check that these are highest weight, in the sense that if you act with the annihilation operator on any of these guys, so these guys, they carry a charge, okay? the charge, basically, if you act with A0 on n, this will give you n over m. So n is an integer. And the charge of the state is just this integer divided by m. You measure everything in units of the charge of the quasio. This is for n bigger than 0. So these are the primary state or highest weight. So to get all the descendants, you pick one of this highest weight and you act with the creation operators. So up to some normalization factor, z mu, right? It's just a product from E to L mu. I will give you the definition of this, of A mu I acting on the highest weight. So as usual, you can write, when you describe a partition, you can write it in occupation number or write it as a partition. So basically, if you want, I use a lot the mi, but you can use the mu I. So let's say in terms of the mi, you have something like this. These are bosonic partition, right? So in principle, I can get two particles here. So you can also write it like this, actually. 1 over c mu product of I A I from 0 to infinity, a minus I mi acting on n. So you can go from one language to another, the occupation number, which is like this, to the partition. So if this will be the partition 3. I have one particle in 3, 2 particles in orbital 2, and 1 particle in orbital 0. So that's the dictionary to go from the partition language to the occupation number language. Right, so the normalization factor, you set it such that n mu, n prime, mu prime is equal to delta n prime, delta mu prime. So you should get exactly the same partition to get, if you don't take the same partition, you have orthogonal states. And L mu is just, it's just a number of creation operators. Right. Here, L mu will be equal to 4. So the last step is to compute the conformal dimension for the descendant. And so if you act with the zero mode of the Virasoro algebra, so it's A0 squared plus AN into the 0. So the conformal dimension of the descendants will be equal to delta nu and mu, with delta and mu being n squared over 2m squared plus mu the norm of mu is just the sum over I equal to 1 to L mu of the mu I. Just the level of the CFT descendant. So now we have the Hilbert space. Good. So let's roll back to the wave function. And now I will do something really, really stupid, but useful. So you start with the wave function, z1, zne. For the time being, forget about the minus e square root of m ne phi 0 v1 v2 v ne. So between each vertex operator, I can insert a complete basis. Sum of all the n, all the mu's of n mu. Let's call this one mu1 and 1. I can do the same here. And 2 mu2 and 2 mu2. And so on. Well, if you do that, what you will get something like this. You get a sum over all n1 up to n e minus 1 from mu1, all the possible partition from mu1 to mu ne plus 1 of something like alpha vz1 n1 mu1 n1 mu1 vz2 n2 c2 n2 mu2 dot dot dot. The last one will be n ne minus 1 mu ne minus 1 vz ne alpha prime. So what have you done here? Well, it's just a product of matrices, right? This is a matrix element, this is a matrix element, and so on. So it's an MPS. It's MPS with two slightly complication compared to what we have described for the AKRT model. Well, the first one is the physical index is actually the particle position. So remember, the physical index for the AKRT model was this, the value of the spin. Let it be +1, 0, -1. Here, it's a continuous parameter. The second issue here is about the bond dimension. So the bond indices are actually, well, you see that there is no restriction for the time being on n and mu. So it's an infinite basis. So you have to deal with a bunch of matrices, actually a continuous number of matrices, and with infinite infinite dimension. So if you want to turn that, so this is called a continuous MPS. It might be useful if you want to do an analytical calculation. Clearly, for people like me that wants to do numerics at the end of the day, it's pretty useless. So we have to do a bit more work to make it like something that we can plug into a computer. So, but basically what we will solve here is the story of the physical index. We will go from something continuous to a discrete version of that. Is it the IMPS just the fact that you use a transfer matrix only? I would say. ID emerge is really that. It's like that's what I will talk about, a single, you taking your system to infinity and basically just dealing with the transfer matrix or the largest eigenstate of the transfer matrix. Okay. I would call infinite dimension another quantity, but maybe you're right. I mean, and the nice thing is CFT is actually quite useful if you want to compute this matrix element. It's like a 3-point correlation function, so you know exactly how it should behave as a function of z. So basically, if you have that, just using the conformal invariance, you will get just z, the conformal dimension, and mu minus the conformal dimension of the vertex operator times minus the conformal dimension of your CFT state, n prime u prime times just n mu v1 n prime u prime. So for these guys, it's actually quite simple to compute the matrix element. And now you know how it behaves as a function of z. For the vertex operator, h, it's actually, so if you have a vertex operator like this, e, q, phi z, conformal dimension is q squared over 2. So we want to go beyond this continuous MPS description. We want to use the orbital basis because this is the one that is convenient to encode in your computer. To write, if you want to write a program to do any numerical simulation about the fractional quantum Hall effect, you will use this orbital basis. So remember that we want to decompose our state psi onto a many-body basis, be it the occupation number basis, CMI, okay, where n orb is the number of orbital. Well, to compute this coefficient, actually, just project the wave function onto this many-body state. Just by definition. And if you have the, so I should be careful about all the normalization factor, but roughly what you will get, the integral over dr1 and e of, so for fermionic state, this is just a Slater determinant, right? So it's z1 star to the power lambda 1. I will give you the definition of lambda 1 in a moment. And e, of course, you have to anti-symmetrize here, star and e. You've got the Gaussian weight, sum over I ci square from 1 to ne, and the wave function. So when I write in the first quantized notation, of course, it's not really helpful to use the occupation number. So I have to go from the occupation basis to the partition, to the occupation notation to the partition notation. Once again, it's the same story, right? If you start, if you have for the MI something like 1, 0, 0, 1, 0, 0, 1, 2, 3, 4, 5, 6. The partition lambda will just be 6, 3, and 0. Here you take the convention that lambda I is bigger or equal to lambda I is bigger or equal to lambda j if I is lower than j, which means that you have to sort your partition from the largest integer to the smallest one. So actually, the anti-symmetrization, you can get rid of it because it's already there for psi. And the rest of the game is almost, you're almost done. Basically, you already see what's going on. I mean, if you look at the vertex operator and the matrix element that you have, you know that you can extract the dependence as a function of z. So it's quite easy in that case to perform the integral over the z. Another way to do that is to say, okay, let decompose into modes my vertex operator. Sum of all n, z to the power n, v, h. So just the mode decomposition of the vertex operator here. And if I plug this formula into the integral that I have here, once you do all the calculation, you will get that the coefficient that you're looking for is actually proportional to, I still have the boundary term, I have the background charge, and I will just pick the proper mode of the vertex operator. So I will get v. You see that you have a power n. So if I do the integral of a lambda 1 of a z1, I will fix the n to be lambda 1 for vz1. Lambda 2 minus h, and so on. Minus e minus h alpha prime. You can make this formula a bit nicer by using the following property about this mode. When you conjugate let's see, yep, reasonable zero mode, you get so it's just another way to rewrite the v minus n. Okay, so if you use this formula here, you can use only v zeros instead of the other modes. 1, prop 2, alpha. I still have, so now I have to be careful, square root of m, n e, that's lambda 1, phi 0, v0, exponential of I minus I, lambda 1 minus lambda 2 over square root of m, phi 0, v0. You can write down the next term, it should be lambda 2 minus lambda 3, square root of m, v0, dot dot dot, v0, and I with this e phi 0 over square root of m alpha prime. As usual, now we have like a big formula, so it's useful to look at a simple case. Let's say you have only two particles. So for n equal to 2, let's take the number of orbitals to be equal to, let's see, 6. Let's look at m equal to 3, so a loft length state 1/3. And I look at the configuration, which is 0, 1, 1, 0, 1, 0, 1, 0. So I just use this formula here. So in that case, lambda 1 will be equal to 4, and lambda 2 is equal to 1. So you just plug all these numbers into this formula here. Square root of 3, get V0, exponential of minus I3, phi 0, square root of 3, V0, exponential of I1, phi 0, the square root of 3, alpha prime. Or if you prefer, you can split each of the phi 0 term and get like alpha exponential I phi 0 square root of 3 exponential I phi 0 square root of 3 V0. Let's put parentheses here. I phi 0 square root of 3 exponential I phi 0 square root of 3 exponential I phi 0 square root of 3 V0 and exponential I phi 0 square root of 3. Now if I call this guy here B0 and this guy here B1, well, I have my matrix product state. Because now what I have is alpha, B0, B1, B0, B0, B1, B0, alpha prime. So this is my matrix when I have an empty orbital, so if I have no electron, and this is the B matrix I have to use if I have one electron. What I've done here is basically, at the beginning, remember the background charge was at one end of the system. So what I've done is to spread basically the background charge everywhere. If you look at the electric charge you have per term, for B0 you get the charge of one quasi-hole, and for B1 you have the charge of one electron minus the charge of one quasi-hole. Or if you prefer, the charge of one quasi-hole minus the charge of one electron. And you see that I can use exactly the same B matrix whatever the orbital I look at. Okay? I'm not cheating here. You have to be a bit more careful if you want to do that on the plane, on the sphere. You have normalization factors. If you look on the cylinder, you can still get exactly the same B0 and B1 matrix whatever the orbital you look at. Or if you look at a thin annulus, for example. So now, remember the story of the continuous MPS, that the physical index was continuous. Now we have a discrete index, can be 0 or 1. So it's really nice if you want to plug that into the computer. There is still one issue. Unfortunately, this is a matrix, right? So I have to insert this complete basis to get the matrix element, which means that I have to compute all these matrices elements, B0, say n of n mu and prime mu prime. So in principle, I have an infinite number of matrix elements to compute. It's an infinite matrix. So remember, that's my auxiliary space. That's the bond indices. So when if you do the orbital entanglement spectrum, the orbital entanglement spectrum, if you remember the first lecture or the second lecture, I've shown you the relation between the MPS and the entanglement spectrum, showing that the number of levels that you have is directly related to the bond dimension. So if you want the Hilbert space for the bond dimension of the orbital entanglement spectrum is the CFT Hilbert space. So that's why you get this counting, this 1, 1, 2, 3, 5 counting. Fix n. So look at highest weight and count at each level how many states you get. Well, you can do this exercise quite quickly. So let's call this mu, and let's look at the states. So if you start at level 0, this is there is a single state. So you have only one state here. At level 1, well, the simplest thing that you can do is to act with a minus 1 on n. There is. Remember that this guy here is just the sum of the mu I. So the smallest thing that you can do is just to get mu I equal to 1. And there is a single way to do that, which is this one. Now let's look at the next level. Well, you can act with a minus 2. Or you can act with a minus 1 to the square. Give you 2 states. I know you will love it. So let's say now level 3. Oh. 1n and a 1 cube acting on n, 3 states, and so on and so forth. So you get, that's the edge mode counting. Nothing surprising here. Remember, the CFT of the edge is the CFT of this free Carroll boson. So that's why you get the, that's what you observe in the entanglement spectrum. What you observe is actually the CFT Hilbert space. Once again, that's for the levels, right? I didn't say anything about the energies. The claim, or the conjecture actually is, so to be precise, the real space entanglement spectrum, if you write down remember yesterday we talked about the entanglement matrix. If you cut your system into 2, the conjecture is that for the real space spectrum, rho A should be actually just the spectrum of the CFT. If you do that, you will see that, well, this is a linear spectrum, basically. It's a function of mu. Right, so it's a spectrum of the edge. It's a conjecture. I don't think there is a rigorous proof that this is what you should get. For the orbit entanglement spectrum, it's a bit more tricky. There is no clear, clear relation between the zero mode of the Vier's algebra and the entanglement Hamiltonian, and in some cases we know that we have corrections to this, which are not, it won't screw up this counting, but it might screw up the fact that you have strictly a linear dispersion relation. The nice thing of the orbital entanglement spectrum compared to the real space one, it's easier to compute numerically, and in terms of getting the information, like if you want to identify the CFT, it will give you the same result. So it's a good idea first to look at the orbital entanglement spectrum and then to move on to the real space if you need more quantitative results. Okay, so maybe one last thing. Right now, I didn't say, I told you that we have an infinite matrix. Once again, in a computer, you won't be able to put an infinite matrix. You have a finite amount of memory. So you will need to do a truncation in your Hilbert space, right? Actually, the truncation in the charge is actually quite trivial, just by the constraint that you start from a given charge sector, and you should go back to the same charge sector. So the alpha and alpha prime, they have the same charge, or plus or minus, depending if you add excitation at the end. But still, it's a finite difference. So the charge will be constrained. But in principle, you have to go through all the partition. So it means that if you do any numerical calculation, you will have to put a cutoff. So what does it mean to put a cutoff here in the CFT level? Roughly speaking, the n and mu, you can relate that to the NA, the number of particles that you keep in the region A, and the angular momentum LZA. So basically, if I fix NA here, you can think about LZA or think about the level mu. So that's the entanglement spectrum for a fixed NA sector. So basically what we will do is we will truncate the CFT. We will truncate it like this. Truncating the CFT is equivalent in the entanglement spectrum to truncating momentum. So you can claim, well, that might be like, I mean, if you do de-emergy, usually what you do is to say, okay, I have my reductivity matrix, and I will keep only the highest, the most important part of the wave function, meaning the largest eigenvalue within the reductivity matrix, which, to think about the entanglement energies, you will keep only the low energy part of your entanglement spectrum. But now you have I mean, if you think that the entanglement spectrum should mimic the edge mode, not only in terms of counting, but in terms of dispersion relation, well, then you have a linear relation between the entanglement energies and the momentum. So cutting in momentum in the entanglement spectrum or cutting in energies, it's actually the same thing. So of course, the truncation that you have to apply depends on your system size. Remember, I was talking about the cylinder and how the shape of the orbital entanglement spectrum will change when you change the perimeter of your cylinder. If you have a thin cylinder, then the slope is very high, which means that in terms of truncation, you will get something like this, and you can keep only a few of the first momenta. If you increase the size of the system, then the slope will go down, and you will have to push much more your cutoff in momentum. But it works pretty well. If you do numerics, if you compute anything like correlation length, braiding, or whatever, for the Lofgren state, you can go well beyond exact diagonalization, and you will get all the nice results that you want, even if you have a truncation within your CFT. There is no free lunch, right? Remember that the AKRT, it was a 1D system gap. There was only 2 levels, whatever the way you cut. Here, if you increase your system size, first you will get many, many NA sectors, and you will get more and more levels. Remember that the entropy is obey the area law, so it will still increase with the perimeter of your system, which means that you will get more. You still have more and more entropy. So you will still be stuck to very moderate system sizes compared to what you can do for 1D gap phases. But it's much, much better than what you can do in terms of exact diagonalization. So maybe to summarize in 2 words, or two sentences. The first one is, entanglement spectrum is a tool. It's a nice one. It's quite easy to implement in terms of code. If you want to probe some emerging phase in your microscopic model, you should really use it. It doesn't take that time to do the code and check what's going on. And each time you observe, maybe 3 things. So the second thing, cut your system in different ways. Depending on the way you cut, you might get different information about your system. And finally, each time you observe that you get much less levels than what you expect for a random state, there it means that there is some nice structure going on in your wave function. And maybe it's worth, you should maybe look at matrix product states and see if you can do something nice. Okay, that's it. Thank you. Any questions? Yep.
this that have an infinite dimension, an infinite correlation length? As the bond dimension sort of tells you how much information you can transport to the next side and the side beyond and so on when you let it go to infinity by using this construction. Because there's something that sort of rang a bell in the back of my mind when you mentioned this, that the bond dimension is infinite. That there are some ways to also describe systems with
Well, it depends. If you think about 1D system, 1D critical system, people do D energy all the time. In principle, you also need an infinite bond dimension for these guys. Now, if you ask me about 2D gapless phases, that's going to be tricky. I mean, just in terms of complexity, maybe you for sure you may be able to write an MPS, but it won't be as efficient as the exact diagonalization. That's the point. Maybe you can. I don't say it's worthless, because sometimes you can organize your information in a slightly different way and you can still compute things, but quickly you will be dead because of that. You will still get a volume law. So you will be exactly in the same regime than the exact diagonalization. So in terms of numerics, I don't think that you can really go beyond that. For 1D critical systems, somehow 1D critical systems like 2D gap phases in terms of complexity. A bit less actually, because it's a log L and not an L. I think it's lunchtime, so unless you have questions, but you can, I'll still be here for 5 minutes. So if you have questions, just come right now.